Today we're looking at linear programming. It's a great application for linear relations. Linear programming was developed in the 40s during World War II to really make full use of factories. And what the situation was that there was a whole heap of constraints placed on these factories in terms of how much stuff they could output, and what they wanted to do was look at the best possible configuration in terms of hours and things like that to produce the most amount of stuff, munitions and whatnot. So in mathematical technique used to solve real life situations where a particular quantity is to be maximized or minimized. We'll talk more about this later. Let's have a quick look at how these relate to linear functions. They're different. So linear programming doesn't look at linear functions, it looks at inequations. But let's look at a function first of all. So remember that these functions are satisfied only when the coordinate point being tested is on the line. That's the only time it's satisfied, is when the coordinate point is on the line. So let's check out whether these two coordinate points here satisfy this function by substituting them in. Remembering that this is the x coordinate and this is the y coordinate. So let's stick those into this function here. So I've got 6 equals 2 times 1 plus 4. 6 equals 6. Bingo. It does satisfy it because it's on the line. Okay. Now I'll be willing to bet this one does not satisfy it. That is, it's off the line. So let's just try it out. 5 equals 2 times 5 plus 4. 5 does not certainly equal 14. This is not true, and that's because that coordinate point there is off the line. Let's check it out. 5 comma 5 is over here. Right? No way that can satisfy this particular linear function. So what we know about linear programming, it involves unknown quantities that have restrictions or constraints that are represented as inequalities. I'll show you one of them in a second. We can still sketch inequalities just like we can sketch a linear function. So we can graph them on a Cartesian plane, and these are satisfied coordinate points in an area that's bordered by the boundary line. So this would be an example of a boundary line along here. And this would be coordinates on this side or on this side that satisfy it, and even the line itself in some situations. Again, we'll talk more about that. Okay, let's have a look at this table here and some terminology. Linear inequalities represent relationships where there are multiple values of the dependent variable y for each value of the, and look, this should say independent variable x. So remember, for a linear function, only one value, for example, this particular coordinate pair satisfy, but there's many ones that satisfy these linear inequalities. Okay, now boundary lines are solid. That is, I draw a solid line when I see a greater than or equal to, a less than or equal to, or a greater than or equal to sign in the inequality that I'm sketching. Conversely, if there's a less than or a greater than sign, I represent the line as a dotted line, because what I'm basically saying is that the values on the line itself are not included. The line itself isn't included in the inequality. Now, to work out which side of the line or the boundary line that is relevant to me, I use a series of test points. Okay, and I'll show you how I use these test points a little bit later on. We also use a key. That is, we either shade the region required, that should say region, there should be an N in there, or so we either don't shade the region required or we do shade the region required, and we'll tend to use this particular option, that is, we do not shade the region required. Let's keep going to the first example. So let's have a look at this scenario. We've got a number of t-shirts being produced, and we're saying that X must be at least 20. That is, we must produce at least 20 t-shirts. I don't know, for whatever reason. So we can represent that with this particular inequality here. X is greater than or equal to 20. So the first step we use is we decide from the inequality whether the boundary line is drawn as either a solid or a dotted line. Now I've noted that there's a greater than and equal to sign, so this is going to be a solid line. Okay, so it's really important that we remember that. Now, identify the equation of the boundary line and find 2 points in order to sketch the line. A great way of thinking about this is to just consider it as a standard equation. That is, to sketch x equals 20. Because remember, all we're doing is we're sketching the boundary line now. Now, well, from experience, we know that this function here is the function x is always 20. So that's just a vertical line where the x coordinate is always 20. So I can mark in one there and perhaps one there. Let's draw a straight line. Now I've got no ruler, okay, but that's my best attempt at it. Alright, I'm going to put some arrowheads on that, and now that's that part done. We've sketched the boundary line using the 2 points. So they are my 2 points. When y is 5, x is 20. When y is 0, x is 20. Now, look, what we've got to do is we're going back to this inequality now, because this function, the only function I've sketched so far is x equals 20. We want to sketch the function x greater than or equal to 20. So what we're going to do is use a test point not on the line to identify which side of the boundary line satisfies the inequality. So this is the tricky and the new part for many of you who are doing linear programming for the first time. So traditionally, the test point that we use is a point at the origin, 0, 0. The reason is that 0 is a really easy number to work with, and it's a great way of testing the inequality. So let's write down the inequality, x greater than or equal to 20, and I'm using the test point 0, 0. Okay, so simply I sub in 0 for x. There's no y value, so I don't need to worry about subbing that in. So 0 is less than or equal to 20. And now I ask myself a question. Is this statement true? Is 0 greater than or equal to 20? Well, I know that this is not true. Okay, so this side of the line, the boundary line, basically is the part that is untrue, that we do not require. This side of the line over here is what we do require. So what I'm going to do is shade the region I do not require. Okay, and I'm going to do that by a series of lines like so. Okay, so now we're shading the side of the boundary line that does not satisfy the equation. So what we've done is left the region required unshaded. Okay, that's all good. This is x greater than or equal to 20, and we've got rid of the rest of it. Okay, so we've done that. Alright, the final part that's really important, we need to add a legend to the graph indicating that the region required is not shaded. So I simply do that by drawing a box like this. It's got to be more of a square than what I've just done, and I write the words region required. Okay, so that means that the unshaded part is the region we require. Remember, it can be the other way around. We just use the convention of that we do not shade the region require for much of the stuff that we do. Okay, well, let's have a look at this one now. So what they want us to do is sketch this particular function. Okay, y take 4x less than 8. So the first thing I'm noting is, will the boundary line be why will the boundary line be dotted? Because it's a less than sign. So it's dotted because it's a less than sign. Find the coordinates of 2 points that belong to the boundary line. So this is the plethora of ways you can find 2 coordinate points. It's up to you how you do it. What I'll do is I'm going to write my function down, less than 8. And I'm going to just, because remember, all we're doing is sketching the boundary line, so we're allowed to just do the boundary line by saying that it equals 8, because remember, all we're doing is the boundary line. Y equals 4x plus 8. I've just transposed it to make it into y equals mx plus c, or into y equals mx plus c form. Okay, so now that allows me to get my first point, which is 6, 7, 8. Okay, which is the y-intercept I'm getting from there. Now, what I'll do is I'll get the x-intercept now. Couple of ways of doing that, so you could try many different ways. I'll get the x-intercept when y equals 0, so 0 equals 4x plus 8. Let's take 8 from both sides and divide by 4. X is negative 2. So that coordinate point is negative 2, 0, and that's there. Okay, draw the boundary line on the axes provided. Now I know that the boundary line needs to be this dotted line. Now you'll forgive me for this. It's hard to do with a stylus. Okay, you're going to do this with a ruler. That's the best I can do for you. Okay, so there's my boundary line. Okay, so we've done that. Now let's use a test point to determine the region required. So because it doesn't go through the origin, 0, 0, I'm all good to use that. Remember, if the line does go through 0, 0, use a different point, test point. That is, I tend to use one, you know, a situation where there's a 1 in it, or -1, or something like that. Just an easy coordinate point to work with. So I'm going to use 0, 0. Okay, so I write my function y take 4x, or inequation I should say, and I sub in 0. So 0 take, well, it's 4 times 0, which is 0 less than 8, 0 less than 8. So now what I do is I ask myself, is this true? Is 0 less than 8? And it certainly is. That's true. Okay, so basically that test point indicates that this side of the graph or the boundary line is true. Therefore we can assume that this side of the boundary line is not true. That is, we don't want it. So I can shade it out. So I'm shading it out now. Okay, so shade the side of the boundary line that is not required. Done. Now insert the key for the inequality. So we're just going to put a box in and say this is the region required. Okay, so we've done our key. It's important to be mindful that the region required can be shaded if the legend indicates that this is the case. VCAR often do this in questions, and I'll explain why they do it and then we do it a little bit differently. It's a really easy thing to explain a bit later on. This is an example of a question that you might get. Which of the graphs below, shaded region is the region required, best represents y greater than 3x take 4? Alright, so what I'm looking at in this is we've got a greater than sign. Okay, and that means that the line has to be dotted. So this one's out, and this one's out. Okay, and now, because I can see basically this is the same function or same boundary line, just left side shaded or right side shaded, what I'm going to do is use a test point. My test point is 0, 0. Y greater than 3x take 4, and I'm subbing in 0, 0. 0 greater than 0 take 4, 0 greater than -4. So is 0 greater than -4? Well, this is in fact true. It's a true statement. But this situation indicates that we're shading the region required. Okay, so because that test point came from there, okay, and in this graph it came from there, that means that this side of the function is the one that we want to shade. It's the region required. That's why D in this example is in fact true. Okay, so more on that later, but really, really important, girls, that you can happily sketch functions like this to get them to look like that, using 2 points and shading, so test point. Okay, and just going back to it, the key is with test points is you use 0, 0 in most situations, but if the line goes through the origin, then you want to use a test point that's not on the line itself. Okay, so 1, 1 is a suggestion. It might need to be 1, 2 depending on the function, but 1, 1 is also a really helpful one. Okay, so for the first part of the double, I want you to do these questions here from 8A. Ms. Abby will be in the second part of the double to go through graphs of simultaneous linear equations and inequations. So she'll be there for that. So good luck with that, girls, and I hope that goes well for you.